There's a mystery buried deep within the history of our planet, one that reaches back billions of years to a time when the sun was a very different star. This mystery is known as the faint young sun paradox. It's a question that has confounded scientists for decades. How could Earth, in its early years, have been warm enough to support life? After all, the sun, in its youth, was far weaker and cooler than it is today. In fact, billions of years ago, the young sun only emitted about 70% of the energy it radiates now. By all models of solar physics, Earth should have been a frozen, lifeless rock, its oceans locked in ice, its surface inhospitable. And yet, that's not what we find. Ancient rocks tell a different story. Isotopic evidence, fossils, and traces of ancient water systems all point to a warm, thriving Earth, one where liquid water flowed freely across its surface and life began to take root. So how could this be? How did Earth manage to stay warm enough to sustain life when the sun itself wasn't providing the necessary heat? This question, this paradox, doesn't just reflect a scientific puzzle. It's a deep philosophical inquiry into how life begins and thrives in the universe. Could Earth's story be a unique fluke, or could other planets around dimmer stars one day be found to harbor life as well? What lessons can we learn from our own beginnings, and how might they guide us in the search for life beyond our solar system? Let's explore this paradox and see what answers, or new questions, emerge from this cosmic enigma. Imagine Earth as it was over 4 billion years ago. The planet is still in its infancy, with an atmosphere thick and tumultuous, filled with carbon dioxide, methane, and other gases spewed by constant volcanic activity. The oceans, though forming, are young, their waters swirling across the land as the planet's surface undergoes constant change. It's a harsh, alien world, yet it is teeming with the potential for something greater. The sun, though, paints a different picture. The star at the heart of our solar system, young and evolving, shines much more dimly than it does today. Its brightness is only 70% of what we now see. This would suggest, by conventional understanding, that Earth's surface temperature would have been far below freezing, too cold to support liquid water, and certainly too cold to sustain life. But there's the catch. Our planet wasn't frozen. The first oceans didn't freeze over, and the earliest signs of life, microbial life, started to appear. This contradiction, this paradox, begs a profound question. What was it that kept Earth warm enough for life to flourish when, by all logic, it should have been locked in ice? To solve this riddle, we turn to Earth's early atmosphere. It was quite different from the oxygen-rich atmosphere we breathe today. Instead, it was thick with greenhouse gases, carbon dioxide, methane, and water vapor, all powerful heat-trapping agents. Think of them as the planet's natural heat shield. In the modern world, the greenhouse effect is a term often associated with the global warming concerns of today. But back then, these gases served as Earth's lifeline. Even though the sun was weak, the powerful greenhouse gases in the atmosphere would have trapped heat, preventing it from escaping back into space. This was a more intense greenhouse effect than the one we experience today, one that kept Earth warm enough for liquid water to exist and life to take root. It's fascinating, really. The early Earth, with its volatile atmosphere, was like a giant pressure cooker, trapping heat and providing the conditions necessary for life to evolve. If the sun had been as bright as it is now, would that have interfered with the delicate balance? Would Earth have been too hot, too volatile to support life? In this light, it's almost as if the weaker sun allowed the planet to remain in just the right condition for life to take hold. The greenhouse effect wasn't just a passive player. It was an active participant in shaping the conditions that gave rise to life on Earth. While the greenhouse effect remains one of the primary solutions to the paradox, there are other possibilities to consider. One theory takes us to the sun itself, specifically, its behavior in its younger years. When the sun was just a few million years old, it was likely much more active than it is today, with frequent solar flares and intense bursts of radiation. Some scientists believe that these solar bursts could have provided just enough additional energy to keep Earth warm, compensating for the sun's overall dimness. Imagine the young sun, full of violent solar flares, energetic outbursts, and intense radiation, beaming its energy across the young solar system. These energetic bursts might have provided intermittent bursts of warmth, preventing Earth from freezing even when the sun's constant output was low. In a way, these explosive events could have acted like nature's backup plan, providing bursts of energy to sustain early life. Another explanation involves tidal heating, the energy generated by the gravitational forces between Earth and its moon. While this effect is more subtle today, in Earth's youth, the moon was much closer to the planet. The gravitational tug-of-war between the Earth and the moon could have generated significant internal heating in Earth, particularly in the early, volatile crust. This heat, emanating from the planet's interior, could have contributed to keeping Earth's surface warm enough to support liquid water and life. In essence, tidal heating could have been the planet's internal thermostat, maintaining the warmth required for life to evolve. But not all scientists agree that Earth was fully thawed during its early years. Some propose the snowball Earth hypothesis, suggesting that the planet may have been completely covered in ice at certain points in its history. Earth, then, would have been a frozen, snowball-like world, a stark contrast to the thriving world we think of today. However, even in this frozen scenario, life may have found a way to survive. Life could have persisted in the regions around the equator, where the ice was thinner, or in the deep oceans, where geothermal heat from volcanic activity could have created refuges of warmth beneath the ice. The Earth may not have been a warm, lush paradise at all times, but pockets of liquid water, sheltered from the freezing cold, could have provided the environment necessary for the first life forms to emerge and evolve. The faint young sun paradox is not just a puzzle for Earth scientists. It has profound implications for the search for life beyond our planet. If Earth could sustain life despite a weaker sun, could there be other planets orbiting dimmer stars that could support life too? Could moons of distant exoplanets, bathed in the faint glow of their parent stars, harbor conditions suitable for life, as Earth did in its early years? This paradox teaches us an important lesson. Life may not require the exact same conditions that we find here on Earth. Perhaps all it needs are the right ingredients and a balance of cosmic forces to thrive. It opens the door to countless possibilities, encouraging us to look beyond the obvious and to explore planets and moons in the most unlikely of places. The faint young sun paradox may never be fully resolved, but its very existence is a reminder of the mysterious and unpredictable nature of the universe. It's a challenge that forces us to rethink the conditions necessary for life, not just on Earth, but throughout the cosmos. As we continue our journey of discovery, this paradox will inspire new questions and new ways of thinking about the forces that shape our world, and perhaps the worlds we have yet to find. In the end, the faint young sun paradox isn't just a scientific puzzle. It's a window into the past of our planet and a doorway to the future of our exploration of the stars. It reminds us that in the search for life, we must be willing to question our assumptions, to look beyond the ordinary, and to embrace the mystery that exists at the very heart of our universe.